Hello, my name is Michel Birler, and this lecture is an introduction to a course on optimization and simulation that I am teaching at EPFL. The lecture will start with a small motivation, and I will introduce the concept of modeling, simulation, and optimization. And I will introduce as well in the lecture an important part, which is data analysis, which is strongly linked to simulation. Well, the motivation is to look into engineering systems in general. So what are engineering systems? I took the definition from Wikipedia. It is a combination of components that work in synergy to collectively perform a useful function. And this is valid for a lot of engineering applications. What are in general the properties that are shared by many engineering systems? They are usually large and complex, and they are designed by human beings in order to perform these useful functions. And they are configurable. And most importantly, they have to interact with the external world. And the objective of what we will try to do is to help engineers to design, configure these complex and large systems while taking into account the interface with the external world. So somehow we may summarize our main objectives as to design these systems, to maintain them, and to operate them. And somehow these three actions are associated with three different time horizons. Basically, a design is for the long term, the maintenance is for the medium term, and the operations are for the short term in general. And in order to do that, we will find the help of an equivalent representation of our system in mathematical equations or in computer codes. And to some extent, I can call these mathematical equations or this computer code somehow the mathematical and digital twins of these systems. And to do that, we will do three things: modeling, simulation, and optimization. Modeling will be application specific. And in this course, we will look at this through case studies. And simulation and optimization are more generic, so this is really the core topic of this course. Modeling, simulation, and optimization. Well, the role of modeling is to represent the engineering system. The role of simulation is more to predict how the system will operate in different configurations. And optimization is about improving the system so that it works better, whatever it means. And how do we do this? Well, basically, the modeling is about capturing the causal effects that are appearing in the system using mathematical equations or computer code. The simulation is about capturing the propagation of uncertainty through the systems. And optimization is about investigating better configurations. I will now go through these three aspects, so modeling, simulation, and optimization, and look at these specific actions like capturing the causal effects, capturing the propagation of uncertainty, and the investigation of better configurations. Let's provide a generic definition of modeling. It's a vast topic, but somehow we can see a system as a black box that is modeled by an equation. And the idea is that this equation takes as inputs several variables and produces also variables as output. One type of variable are called the state variable. They basically describe the state of the system at a given point in time. The y variable are external input that is affecting the system from outside, from the external world. The variables u are also affecting the system, but they are control variables. It means that these are variables that the engineer can control. That's how we will reconfigure the system or make it better by changing the value of these variables. And z is a vector of indicators that provides information about the system, how it performs, how well it achieves the task for which it has been designed, and so on. And the modeling consists in writing this relationship H, which takes X, Y, and U as input and generates the Z as output. Usually this function H has a set of parameters that we denote by theta in this case. Let's take a simple example. Consider a car, which is an engineering system. In this context of a car, X, the state variable, may represent, for example, the speed of the car, or its position, or the position of other vehicles around the car, and so on. So this captures the state of the system. Y captures external influences. For example, it can be the speed of the wind that may affect the speed of the car, or its trajectory. U are the control variables. In this case, the driver may accelerate or decelerate the car. And Z represents the indicators of interest. This can be, for example, indicators of performance, something like oil consumption, for example. The challenge about modeling is to decompose the complexity of these engineering systems. Concretely, this model H, it is not a simple equation. It's usually decomposed to reflect the interactions of the subsystems within the system. For example, if I take again the car, we will develop, for example, a car following model that will capture the speed that the driver would like to reach, so the desired speed of the driver, as a function of the position of the other vehicles around. Then there may be an engine model that calculates the actual consumption of the engine as a function of the acceleration of the car, and so on. So this decomposition is important because this is how we will be able to deal with the high complexity of the system, is by decomposition into subsystem. Maybe each subsystem can be again decomposed into subsystems until we are able to capture satisfactorily the subsystem with a set of equations. As I mentioned, what is important in modeling is to capture correctly the causal effects. This is extremely important because failure to do so may generate wrong conclusions. Why is it important? Because when we will use the model to forecast, that is to see how the system operates in different configurations, well, the main assumption that we will make is that the causal effects will be the same. Causal effects are stable over time and over configuration of the system. Okay, so this is the main assumption when we use models to do forecasting, to do simulation, and to do optimization. We assume that the causal effects that we describe in the model will be constant in various configurations and over time. The variables will change, the X, the Y, the U, they will change, but the causal effects will be the same. And this is not always obvious to capture these causal effects. And in particular, sometimes data can be misleading. So let me give you a funny example here, which is data about chocolate consumption and Nobel laureates. Each flag on this chart has a coordinate. The X coordinate of the flag is the chocolate consumption in kilo per year per capita of the corresponding country. And the Y coordinate is the number of Nobel laureates per 10 million population in the country. If you look at the data, you can see that there is a clear correlation between the two quantities. Actually, you can even calculate the correlation. It's about 0.8. It is actually tempting to draw a line and make some linear regression that would be a model that predicts the number of Nobel laureates as a function of the chocolate consumption. It means that if I have a new country, I just calculate the number of chocolate consumption and it will give me the number of Nobel laureates. It means also that if I want to increase the Nobel laureates in a country, and I'm a policymaker, I will deduce that by increasing the chocolate consumption in the country, I will increase the number of Nobel laureates. Well, obviously, there is something wrong here. And the idea is that it's not because there is correlation between two sets of data that there is a causal effect. So what's happening here? Well, maybe one explanation would be that the true explanatory variable is actually the wealth of the country. If a country is wealthy, it's likely that the inhabitants will eat more chocolate. And independently, it's also likely that these inhabitants will be more educated and therefore may have a higher probability to get a Nobel Prize eventually. Okay, so the same cause here, the wealth of the country, has two different effects. These effects are therefore correlated, but it doesn't mean that there is a causal relationship between them. And this is extremely important to model it well. So usually data is not sufficient. We need also to use the theory and common sense to make sure that everything is valid. As I mentioned, the model usually has parameters, and these parameters must be estimated to reflect as well as possible the reality. This is called inference. In order to perform inference, we need to observe the system in a configuration that is already existing. And actually, we collect several observations about the system. And these observations basically consist in measuring the value of the variables that are involved, so the x, y, u, and z, in these various configurations. And we have capital N of these observations. Then what we do is that for each of these observations, we compare the predicted value which is provided by the model. So this is it here. So it's h calculated at xn, yn, and un for a given value of theta, with the observed value zn. In a perfect modeling context, well, h should be able to predict zn. We will call the goodness of fit the distance between the two quantities. And I put distance in double quote because there are several ways to actually define the distance. But in this context, let's think about it as a distance. So if it is perfect, I will have 0, and it will increase as imperfection comes into the picture. So dn of theta is the distance between the prediction of the model and the observed indicator zn for a given value of theta. What is inference? It consists in finding the value of theta that I denote theta hat that minimizes the total distance for all the observations between the prediction and the observation. And again, there are many ways to do inference. That's not the point of this lecture. But the idea is that once you have done this, you have h, your model, and you have theta hat, which is the value of the parameters that have been estimated from data. Okay, so now we have a model. We can start using it for prediction and simulation. The idea would be, let's plug values of x, y, and u in the model so that we can predict value of z. Okay? So this is called applying the model. But simulation is more than that. The idea of simulation is to acknowledge the fact that there are a lot of uncertainty in the model. This uncertainty can be due to many things. It can be measurement errors, modeling errors, or anything. Therefore, what I will denote by simulation is the same setup that I presented before, but I have added some noise here. So these are random variables, epsilons, that actually are added to the various variables involved in my model. And now, if you notice, I have denoted all the variables with capital letters. The idea is that a capital letter represents a random variable. So this is what simulation is all about. I consider my model, which is this function h with the parameters theta hat that I have estimated from data. And now I will use it in order to simulate the way uncertainty is propagating through my system. In other words, given the distribution of the inputs x, y, u, and epsilon z, what is the distribution of z? Remember, z is a vector of indicators that are of interest, that will tell me how well my system is working. And because of the uncertainty, this is a random variable, I'm interested in the distribution of this random variable. How does it work? Because h is very complicated, as we discussed before, therefore I cannot just write the equations. So what I will do, I will draw realizations of the inputs of x, y, u, and epsilon z. I know the distribution, so I should be able to draw from this distribution. And this is something that we will see in details in this course. Each realization I denoted by small x r, small y r, small u r, and epsilon z r. So r for realization. And for each r, then I plug this realization into the formula, and I calculate the corresponding output for z, and I denote it by zr. And basically zr is a draw from the random variable capital Z. So the idea of simulation is to generate many draws. Each set of draw will generate an instance for capital Z, zr, and then I will analyze the empirical distribution of these draws that have been generated by the simulator. Okay, so this is how simulation is working. It's about generating draws, applying the model, and then analyzing the data. Yeah, for example, one of these input variables may follow a distribution that is given by a set of dice. And you can think about the simulation as throwing the dice, taking the value, plug it into the model, and calculating the output. Then throwing the dice again and start again and again. It's important to keep in mind that this has to be done many times. So the number of draws is something which is really important. Why? Because the theory tells us that the true distribution of Z will be obtained when the number of draws goes to infinity. Of course, in practice, we don't have time to wait until infinity, and the number of draws will be finite. We will usually call it capital R. And if capital R is too small, basically the simulator is just generating noise, random numbers that do not mean anything. This is very important. And there is actually an analogy with the real world, because you can see nature as also a random number generator. It generates instances of a very complex random variable. This is why we need to perform experiments several times in order to reach valid conclusions. And let's take an example where this is not always correctly done, talking about policy analysis. Indeed, the real impact of a policy is usually difficult to analyze. And it's tempting for politicians to use incomplete results when they are consistent with the expectation to prove, quote unquote, that the policy has the right impact. But this may be an erroneous conclusion if it is based on an insufficient number of draws. Let's look at an example to see more concretely what I mean. Suppose that the mayor of a city that I call Kid City, you will see why in a moment, would like to improve the safety in the city. And to do that, he has commissioned a consulting company that needs to assess the effectiveness of a safety campaign that the mayor has designed. And they propose to use simulation to do so. This is the map of Kid City. And first we need to simulate the current number of accidents for the current year in the city. To do that, they propose to use a simulator, and in particular, they propose to use the dice as we discussed in the previous slide. So they use the simulator, we throw the dice, and we obtain the number of accidents at several locations in the network. So here we have 8 accidents, 5, 8, 12, 7, 3, 9, and 6. Great, so this is the current situation. Now we would like to improve the safety, so to decrease the number of accidents. So the mayor has decided, let's identify the location where we have the largest number of accidents. This is here with 12 and here with 9. So these are the most dangerous spots in the city. And then we will implement some signs that will tell the drivers to drive safely. That's the idea of the mayor. So in our simulator, we put the stickers. We have a sticker here, drive safely. And here we have a sticker that says drive safely. And so the mayor is convinced that by doing this, it will improve the number of accidents. So let's use simulation to see if it is indeed the case. So let's now simulate again the number of accidents after we have put the stickers in place for these 2 locations. So we have thrown the dice again, and here we have obtained 3, and here we have obtained 6. Amazing, so it works. We have indeed decreased the number of accidents on the 2 locations. So putting the stickers there has a positive impact on the safety in the city, which is great. Okay, I'm sure you have understood the fallacy here. Okay, this is a very typical example of a case where we don't use a number of draws which is enough, right? As I mentioned before. Indeed, we use 1. Every analysis that we have done here is based on only 1 throw of the dice. Another problem is that the model that we are using, which is based on the assumption that the number of accidents is based on a pure random process, which is throwing the dice, there is absolutely no relationship in our model between the cause that we want to analyze, in this case the stickers or the signs, and the phenomenon itself. So the model does not capture the causal effects. Okay, so we make basically 2 mistakes. We are using the wrong model, because if we are really interested in the impact of these signs, we would need a model that actually measure the causal effects of these signs. And second, we are using an insufficient number of draws. So these are the 2 major flaws in our analysis. The causal effects are not modeled, and the simulation is performed with only 1 draw, which is definitely insufficient. So what should have been done? Well, at first, as I said, we should have a better model that tries to capture the possible causal effects between the presence of the sticker and the number of accidents. But in any case, we should have simulated the number of accidents many times. So instead of throwing the dice once for each location, we should have thrown the dice 1,000 times at each location. And if we had done so, well, the average number of accidents would have been around 7 everywhere, in every location, and with or without the sticker. It would not make any difference. And actually, we can use then a formal statistical test in order to test the null hypothesis that the sticker has no effect. And actually, the test would never reject this hypothesis. This is the proper way to do it. Okay, so the message is we need to generate many draws. So it means that we will also generate many outputs. We will generate a lot of data from the simulators. And this data must be properly analyzed. As I mentioned previously, the data that are generated by the simulator are instances of the random variable capital Z. Now, we have access to this empirical distribution, and what do we do with this? Well, we may be interested in some indicators associated with the distribution. Well, typically, we may be interested in the mean. In the previous example, I would be interested in the average number of accidents. But I can also be interested in the variance, or in the mode, or maybe in the quantiles. Which one depends on the application. The nice thing is that because I have access to the empirical distribution, I'm able to calculate all these indicators. So how do you do that? Well, if you are interested in the mean, you can approximate it by calculating the sample mean, the mean of the data that you have generated. Same thing with the variance, you can approximate it with the sample variance here. If you want to calculate the mode, you need probably to plot the histogram and look at the mode. There can be one mode or several modes. And if you're interested in the quantiles, you need to sort the data and select the proper quantile. It can be the 95% quantile or the 60% quantile, whatever. But what is important to keep in mind is that there is more than the mean. Something interesting about the mean that I would like to emphasize here is that most models that we are using are extremely nonlinear, and it means that we need to be careful about how we use it. And I took here a nice picture from a book by Savage that says the state of the drunk at his average position is alive, because the average position is the central line here. But the average state of the drunk is dead. So think about it as our model. So my model here is that give me as input the position of the drunk, and the output will be he is alive or is dead. Okay? Now I can do two things. One thing, which is the wrong thing to do, would be to say, okay, well, let's calculate the average position. And in that case, this would be this line. And let's apply the model to see what happens. In this case, the model would tell you alive. But that's not what we need to do. We need to use simulation. So we will draw from this trajectory. And for each draw, we will apply the model. And if we do that, we will obtain, I don't know, this point, maybe this point as well. And then the model will tell us several times the guy dies because he is hit by a car, and sometimes he does not die. And this is the correct way to do it. To put it in a mathematical term, it's important when you calculate the average of z to do it in the proper way. Z is actually defined by the model, so h plus epsilon. And this is what you need to calculate, the expectation of this quantity. It's not valid to calculate the mean of each input, like the expectation of x, the expectation of y, the expectation of u, and the expectation of z, and then to apply the model. This is not valid. So application of the model at the average point is not what we need. The only case where it works would be a linear model. But most models that we will be using are highly nonlinear. So this is why we need to rely on simulation. So this is the first thing to say about the means. Be careful that the average of the output is not the output of the average. But also, it's important to realize that when you generate all this data from simulation, there is more to it than the mean. You have access to the full distribution and you can calculate a lot of stuff. And sometimes the mean is not what you need. Let's take a simple example. So let's consider an intersection with a capacity, let's say 2,000 vehicles per hour. And this is controlled by the traffic light, which is 30-second green, 30-second red, for the sake of the example. The cars are arriving at a constant arrival rate of 2,000 vehicles per hour during half an hour. And then, from time to time, the capacity of the intersection drops for some reason. So let's say that, again, for the sake of the example, with 30% probability, the capacity drops to 80%. Now the question is, in this context, what would be the average time spent by the travelers in this intersection? And we can use simulation to do that. And this is what I've done. I have simulated this setup. And this is the distribution that you get. So this is the histogram of all the realizations of z. So z in this case is the average travel time spent by the travelers in the system. Okay, so each instance is the average of all users of the time they spent in the system. And I represent here the distribution of this average travel time. Now what you see is that this is a bimodal distribution. You have two modes. Why? Well, because sometimes the intersection works at full capacity, sometimes not. And this is basically what is captured by these two modes. So this is when the intersection is working at full capacity. And this is when the intersection is working at 80% capacity. And this happens like 30% of the time. In that case, the travel time increases significantly. So the system is in one mode or the other, and you can see very precisely what is the distribution of these two modes of operation. But now if you calculate the mean of this quantity, you obtain something which is here. and which has actually a quite low probability to occur. This is not what you are interested in here. What you are interested in is these two values, the modes, so one which is here and one which is here. Okay? And again, because you use simulation, you have access to the full empirical distribution. This is relatively easy to do. Okay, so these are what I would call some pitfalls of simulation. The first one is extremely important. Don't use too few runs, because you will lead to erroneous conclusions, as we have illustrated. And you have to keep in mind that sometimes it's tempting, because if the model is complex, the running time is quite prohibitive, and therefore it's tempting to generate partial results rather than no result at all, and to reach conclusions. And as in the example that we have discussed, if the conclusions based on impartial results are consistent with your expectation, you may be tempted to accept them, although they are not necessarily right. And the second pitfall is that there is a tendency to focus solely on the mean. I insist the mean is useful, but it's not always sufficient. It's actually maybe misleading, and like in the case of the intersection. So it's important to look at the entire distribution. And we have a tendency to develop our intuition based on the normal distribution, which is a symmetric distribution. The mode equals the mean, but this is not the case in general. Okay, so with the normal distribution, of course, the mean is extremely important because it's also the mode. But it's not the case for all distribution, in particular for distributions associated with complex systems. Okay, so this is important to investigate the whole distribution, and simulation is actually designed for that because it will generate draws from this distribution. So these are the challenges that we will be dealing with in the course. So how to generate draws from capital Z, which is the key thing. Well, we will also look at how to represent the complex system. So we will focus on H, this model. I told you need sufficiently many draws, but how much is sufficiently many? So we'll have to deal with this question, how large capital R should be. And then we know that by the end of the day, we always make an approximation, right? So the question will be, how good is the approximation? So we will cover all these aspects in the course. Now, before we talk about optimization, I would like to make a small comment, because we will be generating random numbers. As I said, we will have to generate draws, and we will be using a computer for that. And computers should not be random. So there is a mechanism that is implemented in every programming language, which is the generation of what we call pseudo-random numbers. So what is a pseudo-random number? It is a deterministic sequence of numbers which has the appearance of draws from the uniform distribution. And this is basically available in any programming language. So how do they do that? I will not spend too much time on this, but I give you an example of one way to do that, is to create a sequence xn, which is defined like this. You multiply xn minus 1 by a constant a, and then you take the modulo m. And this gives you the next element in the sequence. So this sequence has a period of order m because of the modulo. Therefore, if you want a large period, you need a very large number. And that's usually the case. And in general, we'd select m to be a large prime number. So a typical example would be m would be 2 to the 31 minus 1, which is a large prime number, and a would be 7 to the 5. Now, in order to generate the draws from the uniform 0, 1, you divide each of the xn which are generated by m, and you obtain a number which is between 0 and 1 by design. This sequence will have the appearance of purely random draws. So that's basically how computers generate random numbers. And the first element of this sequence, x0, is usually called the seed in programming language. It means that if you want to replicate your sequence of random numbers, you can set the seeds, and with a given seed you will have exactly the same sequence because it's actually deterministic. Okay, so for the lectures on simulation, this is what we will do. We will look at draws from distribution. We will look at discrete event simulation, that is basically a way to represent the H function. We will perform data analysis, as I mentioned. And then we will see more advanced material. One of them will be variance reduction. It's about how to get the same precision with a lower number of draws, or how to get a higher precision with the same number of draws. And then we will see a quite advanced technique to generate draws from very complex distribution, which is called Markov chain Monte Carlo. And the main reference that I will be using for simulation is the book by Ross that I recommend very strongly. Okay, so this was the bulk part of this introduction, the discussion about simulation and the associated data analysis. So let's conclude this introductory lecture by talking a little bit about optimization in the context that we have defined. When I will talk about optimization, I will make some assumptions. The first one is that the control variable u, which is the one that will allow me to change the configuration of the system, I will assume it's deterministic, okay, in this course. This is the same formula as before, where u now is in lowercase to show that it is not random anymore. And then I will be interested in several indicators associated with the vector z, okay, and I call them z1 to zm. So this could be, I don't know, the mean of something, the variance of something else, the quantile of something else, whatever. And of course, this will be a function of u. Most of the time in optimization, I will combine all these indicators into one of them, f of u. And the idea is that this indicator, f of u, is something that I would like to make as large or as small as possible. And this is really the idea of optimization. I have an objective, so this will be usually called the objective function, and I will try to find the value of u that makes this value as large or as small as possible. But sometimes you don't want to do that, and I will also discuss about what we call multi-objective optimization, where we don't group them into a single indicator, we keep them separate. So this is a little bit more complicated, and I will have a lecture to discuss about that. So if I take the picture that I had before, so now the control u is a deterministic variable, and I will basically consider everything else here as a black box, which is provided by my simulator. So I will run my simulator, and for each value of u which I input, I will get a value of f of u. And now my task as an optimizer would be to find the value of u which makes f of u as large or as small as possible. Usually I will write it like this. In this case I'm talking about minimization, so I will try to make f of u as small as possible. So I will minimize f of u. U is the control variable, it's a vector of Rn, and usually I will have constraints, so because not every configuration is valid. And these constraints will be defined by a set here. So capital U is the set of valid values for the control variables. We will usually call it the feasible set. I will introduce some classical optimization problems, and then I will talk about heuristics, which are appropriate algorithms to be used with simulation. And as I said before, I will have a lecture on multi-objective optimization, which happens very often when we use simulator as well. Okay, in summary, the three pillars of what we do are modeling, simulation, and optimization. For modeling, I emphasize the fact that we need to decompose the complexity of the system, and we need to capture correctly the causal effects. The second thing is about simulation. I emphasize the fact that this is about propagation of uncertainty. I insisted on the fact that it requires many draws, because if not, you make erroneous conclusion. And it's important to analyze the entire empirical distribution. It's okay to calculate the mean, but we should not focus only on the mean. There is more to it than the mean. And finally, optimization is about identifying the value of the control variables that improve the function of the indicators. And sometimes you have the option to do multi-objective optimization that will also be covered in this course. I have included here the various references that I've used in the lecture, and I hope that you will be enjoying the rest of the course. Goodbye.